Okay, everybody, and we're back for part two. For this part of the digestion lecture, we're going to talk about the physiology of the digestive system and then wrap up with a couple conditions. Let me just share it with you. And here we go. All right, so a quick review of the major components of the digestive system. You've got the mouth and oral cavity, then the pharynx, esophagus, stomach, small intestine, and large intestine. Then you also have those accessory organs, the tongue, teeth, and salivary glands that are found in the mouth, and the liver, gallbladder, and pancreas in the abdomen. Remember, the main components are the parts that the food actually passes through and where digestion actually takes place. And the accessory organs contribute to digestion, but the food does not pass through them. Now, when we start to talk about the physiology of any system, we always get started by talking about the functions that that system performs. Most people could tell me off the top of their head that the digestive system is responsible for getting us the nutrients that we need from our food. But that process actually involves 6 separate sort of sub-steps that happen throughout the GI tract. Some of them happen everywhere, some of them only happen in one place, some of them there's some overlap. So you can't really say that these are necessarily presented in order, although they're in order, they're just overlapping. Let's think of it that way. So the overall goal is to break down large complex molecules into the monomers that can be absorbed by the body. And to do that, you have to accomplish these 6 things: ingestion, propulsion, mechanical digestion, chemical digestion, absorption, and defecation. Obviously, ingestion we're only going to see happening at the mouth and oral cavity, and defecation we're only going to see happening at the end of the large intestine. But the others are a little bit more complicated. Propulsion, for example, happens in literally each region of the digestive tract. If it didn't, things wouldn't keep moving along. So we're going to work our way through the digestive tract and talk about where each one of these things take place. I also like to take just a minute to compare and contrast what we mean when we say chemical digestion and mechanical digestion. So mechanical digestion means you're physically breaking down the food from big pieces to small pieces. So that's going to be things like chewing and the movements of the stomach that cause mechanical digestion. Chemical digestion is where we're actually breaking bonds within the material. So breaking down the food with acids, enzymes, and other chemicals that are provided by the digestive system. So let's start in the mouth and oral cavity and just summarize what's happening in each region of the digestive tract. I would recommend that you guys summarize this for yourself. Make yourself a little chart, list off the steps, the regions of the digestive system, and next to each one, list the functions that occur there. Beyond that, I'm also going to have you add a little bit to that a little farther along. I'll explain that as we go. So in the mouth and oral cavity, like I said, obviously this is the site of ingestion. This is where food comes into the system, but it's also where we start both mechanical and chemical digestion. Mechanical digestion is going to start because of the action of the teeth and tongue, and chemical digestion is going to start because of the action of the enzymes that are added to the mix in the mouth and oral cavity. You're going to see as we go farther along that only carbohydrates and lipids begin to be digested in the mouth, not proteins. So you might want to leave yourself just a little bit of space as we move along and talk about the actual process of digesting a bite of food. I'm going to talk about what enzymes are responsible for the digestion of carbohydrates in the mouth and lipids in the mouth. And I'd like you to have you add that into your notes for functions. Propulsion, like I said, takes place in every region. So you should see that listed in every section as we move through, and make sure that you include that as a function for every region. Now, once we get into the pharynx and then the esophagus, we don't really see anything new happening. The food does not spend much time here. So there's no new digestion occurring. The enzymes that were added in the mouth keep working. There's no reason they wouldn't, but they just don't have a lot of time and nothing new is added. So the only real functions that we list for the pharynx and the esophagus is propulsion. Once you get into the stomach, we see a lot more happening again. The food spends a lot more time here. So we still see propulsion happening, of course. We also see both mechanical and chemical digestion. The mechanical digestion is due to the churning and mixing that happens in the stomach. The chemical digestion is primarily focused on proteins and lipids. We do not see any digestion of carbohydrates in the stomach, and that's one of the reasons why high carbohydrate meals move through us so quickly and leave us feeling hungry sooner, because it doesn't need to stay in your stomach to be digested. Proteins and lipids do. And again, you'll want to leave yourself some space to make some notes about what kind of enzymes are involved in that process when we get into the point of talking about our bite of food reaching the stomach. We do see a small amount of absorption happening in the stomach, but really not of nutrients. So typically, I don't list absorption as a function of the stomach. The only reason things get absorbed in the stomach is if they're fat soluble and the food is just sitting there long enough, or the material is sitting there long enough. Anything that's fat soluble can move across the lining of the stomach. So that's going to include things like aspirin or alcohol or other medications. And a lot of those things also tend to be irritating to the stomach lining because it wasn't really designed for absorption. It just absorbs because it's there. There are several accessory functions of the stomach. What that means is these are not listed as key functions of the digestive system, but they're things that the stomach does for us. For example, it can store ingested food if digestion has to be kind of put on hold because, for instance, a stress response, or just simply because you're going to see that the food in the stomach can't all move to the small intestine at the same time. And it also produces a material called intrinsic factor. Remember, that was one of the products of the parietal cells, which are going to help us absorb vitamin B12 later in the small intestine. Speaking of the small intestine, the functions in the small intestine, again, obviously we have propulsion occurring here, as we have in all regions. We do see a little bit of mechanical digestion, but really if something's not physically broken down by the time it gets to the small intestine, it's probably not going to be. The main thing that we see here happening is a lot of chemical digestion of all three nutrient categories, and we finally start to see the beginning of absorption of those nutrient monomers into our system. In the large intestine, there's really no new digestion. If something's not digested by the time it reaches the large intestine, it's probably not going to be. But we still have a lot of absorption taking place, especially of water and salts, to help us to form a compact waste product. And speaking of that, defecation obviously only occurs in the large intestine. The large intestine has some accessory functions similar to what we saw in the stomach. In the large intestine, we find bacteria living there that serve a purpose for us. They actually help us with vitamin metabolism. They feed on indigestible carbohydrates from our diet, things that we were not able to digest or get any energy from. They are. And they do it through a process known as fermentation, which produces gas. Now, you might think that that's something you don't want. Nobody likes having gas. But the bacteria are earning their keep by making vitamins that we need, which we can then absorb along with the water and electrolytes from the large intestine. All right, so I said we were going to follow a bite of food through the system, and that's what we're going to start with now. So let's imagine you're having a nice lunch or dinner of pizza. Pizza is a great food to talk about when we talk about this process because it has everything. It has fats, it has protein, it has carbs. So we can eat a pizza and think about the action of all of these different enzymes in all the regions of the digestive tract. The first step in getting something into your digestive system is the process of deglutition, which is just a fancy word for swallowing. In deglutition, you have to first compact the food into a bolus. You might not realize that you do this, but pay attention sometime when you're chewing. And your tongue actually works to take the food and kind of pack it together into a swallowable chunk. Babies have to learn how to do this. And that's why initially when you try to feed a baby solid food, many times their tongue pushes it out of their mouth because it just hasn't gotten used to this idea of forming the bolus, pushing it to the back of the mouth and triggering swallowing. There's 3 phases to the process of deglutition. The first phase is called the buccal phase, and it's voluntary. So you have control over this. If you're in this phase and I tell you to stop, you can stop and not swallow whatever it is. This is where the bolus is created, and the tongue takes it and pushes it to the back of the throat into the oropharynx. The second phase is called the pharyngeal phase, and everything from here on in is involuntary. You can't stop it once it's started. Once the food hits the oropharynx, it triggers the beginning of the pharyngeal phase, and it pushes the food down through the pharynx to the esophagus, and then we enter what's called the esophageal phase, where food passes through the esophagus down to the esophageal sphincter, which will open, and then the food can enter the stomach. So those last two phases are involuntary, meaning you have no control over starting or stopping them, and you don't have to think about making them happen. Now remember, in talking about the functions of the digestive system, we started both mechanical and chemical digestion in the mouth and oral cavity before we actually swallow the food. The mechanical digestion was caused by the teeth chewing our food and the tongue breaking it up, and the chemical digestion was caused by two enzymes. Remember, I told you back in the previous list that carbohydrates and fats begin their digestion in the mouth. So there's two enzymes involved. Salivary amylase begins the carbohydrate digestion, and lingual lipase begins the digestion of fats. Salivary amylase comes from the salivary glands, and lingual lipase comes directly off the surface of the tongue from glands on the tongue. There's not a significant amount of either carbohydrate or fat digestion happening in the mouth, and really most people believe that the little bit of digestion that does happen in the mouth mostly enhances our sense of taste of these substances. And sugars and fats specifically are great energy sources. So you want to have a strong sense of taste, a strong attraction to these evolutionarily, because that you're going to have better survival. You're eating food that's providing you with a lot of energy. Now, obviously, in today's modern American diet, carbohydrates and fats are not lacking and not rare, but it does explain some of our taste preferences and why some people have difficulty controlling their intake. Once the material travels through the pharynx and the esophagus, where, as you recall, nothing new is happening, it's going to reach the stomach, where we see more mechanical and chemical digestion taking place. In the mechanical digestion is really dependent on the churning of the stomach. So you've got the muscles of the muscularis externa that start to involuntarily contract every 15 to 25 seconds. So that's 2 to 4 times a minute. This is going to mix the incoming food with acids and enzymes and saliva and everything else and create a liquid paste that we call chyme, which is then going to move through the rest of the digestive system. The chemical digestion that's taking place, remember, focuses on proteins and fats. Pepsin breaks the bonds between amino acids and converts big proteins into smaller proteins or even large peptides. It does not break them down enough to actually be absorbed into the bloodstream. The hydrochloric acid that's present in the stomach is going to provide an optimal pH for the pepsin, and it's also going to help in protein breakdown. The gastric lipase that's produced in the stomach, also by those chief cells, remember the pepsin and the gastric lipase are both coming from the chief cells in the gastric pits, is going to start breaking down lipids into triglycerides. But triglycerides are not small enough to be absorbed either. So nothing is being broken down small enough to actually go through absorption, but it is starting the process of breakdown. So one of the things we have to think about is, how do we control these secretions of the stomach, the acids and the enzymes? We don't want to be making them when we're not using them because that's wasteful and irritating to the stomach lining. So you only want to be making them when you need them. And so how is this controlled? Well, it turns out there's both nervous control taking place as well as endocrine control taking place, which shouldn't be a big surprise since those are the two main control mechanisms of the body, and they work together to control most things. There's 3 phases to the process: the cephalic phase, the gastric phase, and the intestinal phase. Cephalic means head, gastric means stomach, and intestinal obviously refers to the intestines. Remember, though, as we go through these, that in each case, it's talking about how that part of the body is influencing the stomach. So the cephalic phase means, how is the head influencing the stomach? okay, in the gastric secretions in the stomach? How is the stomach in the gastric phase influencing the secretions? How are the intestines influencing the secretions in the stomach? It doesn't really have anything to do with what's going on in the intestines. So the cephalic phase actually happens usually before food has even entered our stomach. It's triggered in a number of different ways, for instance, by seeing food, smelling food, tasting it, or even thinking about food. There's two different pathways depending on how close to you the food is. So if you're just seeing food or thinking about food, you might not actually be all that close to the food. Maybe you're seeing it on television or seeing it in a picture. So it's not necessarily in the same room with you if you're just seeing it or thinking about it. If you're tasting it or smelling it, it's probably pretty close by. So these have two separate paths. Sight or thought of food first has to go to the cerebral cortex where we process information. So that's going to be a longer path. Taste and smell go directly to the hypothalamus and the vagal nuclei in the brainstem, in the medulla oblongata region. If you had to see it or think about it, it goes to the cerebral cortex first before it goes to the hypothalamus and vagal nuclei. But either way, the outcome is the same. A signal goes through the vagus nerve and tells the stomach to increase gastric secretions. What it's doing is it's preparing for the arrival of food. We've all probably experienced the cephalic phase in action without knowing it. If you ever went into a restaurant with a friend, you weren't hungry but thought you'd just sit with them, but when you see and smell the food, all of a sudden you're hungry. That's your cephalic phase kicking in. It can even happen late at night when you're up studying and watching television and you see that ad at 11:30 at night for pizza and they stretch out the cheese and make it look all amazing, and all of a sudden you're hungry when you weren't before. And that again is the action of the cephalic phase. I said that it should occur before food has entered the stomach. One of the reasons that Americans have so many digestive disorders is that we tend to eat on the run. So it could very well be that you would grab something to eat when you're not particularly hungry already. You hadn't really been thinking about food. You hadn't really been seeing it or smelling it. Take a bite and swallow. So the first sense in that case that would trigger the cephalic phase is just taste. In that case, the stomach may not have time to adequately prepare before the food arrives, and it could lead to indigestion. So you always want to be careful to not rush when you're eating if possible. In the gastric phase of control of gastric secretions, this is where the stomach takes over its own regulation. So once the food has entered the stomach, there's a number of reflexes that will continue the production of stomach juice so that it will be produced adequately to digest the food. The first reflex relies on stretch receptors that respond to distension of the stomach. The second reflex relies on the presence of chemoreceptors that detect the presence of proteins and food in the stomach. Hold on one second. I'm actually getting a call right now from our college telling us that they're closing early today. So hold on one second.
April 1st, 2017. All classes are canceled Friday evening and all day on Saturday. This is an MCC weather alert. Due to inclement weather, Manchester Community College will be closing at 5 p.m. today, Friday, March 31st, 2017, and will remain closed all day Saturday, April 1st, 2017. All classes are canceled Friday evening and all day on Saturday.
All right, sorry about that. I couldn't get to my phone to turn off the answering machine, so you guys probably got to hear that message. So let me just repeat what I said before in case you couldn't hear me over the phone ringing and the message. So you have two sets of reflexes that control the production of stomach juice during the gastric phase, where the stomach is controlling itself. The stretch receptors sense how full the stomach is, and the chemoreceptors detect the presence of protein in the stomach. Because remember, that's one of the primary things that the stomach is focused on, is the digestion of proteins, okay? So if it's the stretch receptors, I'll start with the chemoreceptors. If it's the chemoreceptors, when they sense protein still present in the stomach, send a signal to the G cells. The G cells, remember, those are those enteroendocrine cells that release their secretions into the bloodstream. They release gastrin, a hormone, into the bloodstream, and gastrin is going to promote the increase of gastric secretions. So that's a hormonal path for that reflex, an endocrine path for that part of the reflex. The stretch receptors sense the stretch, the distension, or how full the stomach is, and they have a neural path. They directly tell the stomach to increase gastric secretions. So if you are either still really, really full, the food hasn't been completely reduced to chyme, or if you still have undigested protein in your stomach, either of those things is going to trigger the stomach to continue digesting, to keep working on it. All right, and hopefully that's going to reduce the volume of the stomach and reduce it to that creamy chyme with all partially digested protein before it gets moved along to the small intestine. Now, the only time that this kind of fails you, right, is when you eat a small meal that's all carbohydrates. You might feel full initially, but because it doesn't cause a lot of stretch on the stomach and it doesn't trigger the chemoreceptors because there's no protein present, it's going to pass through the stomach very quickly. It's not going to be encouraged to stay and digest. And that's why those high carbohydrate meals tend to not make us feel full for very long. Now, this last phase, I want to stress again, we're not talking about digestion in the intestines. We're talking about how the intestines take over control of the stomach, okay? Because now it's time for the food to start moving into the intestine, but that doesn't mean we want it all at once. Every time the stomach contracts a little bit of that low pH chyme enters the small intestine. When it does, it actually causes an initial release of gastrin. That might not seem like it makes sense at first because you think, well, if it's ready to move into the small intestine, why do we want to continue to encourage the stomach to release secretions and keep churning? But like I said, you don't want it all at once. So the intestines are going to tell the stomach, hold on to that, keep working on it a little bit. And it also triggers something called the enterogastric reflex. In the enterogastric reflex, the pyloric sphincter closes tightly. That was that sphincter connecting the stomach to the small intestine. Most of the time, it's loosely closed. So if the stomach churns, a little bit of chyme can get through. But once a little bit of chyme has gotten through, the small intestine needs time to deal with it. So it shuts that door tightly. It also shuts off the cephalic phase and the gastric phase. So it's going to shut off the vagal nuclei of the medulla. So that means that if you're still seeing, smelling, thinking about food because you're still sitting in the restaurant or still watching television and seeing ads or whatever, it's not going to continue to control your stomach. It also inhibits the stretch receptors of the stomach, okay? So just because your stomach is still really full doesn't mean that they need to be telling the stomach to continue gastric secretions. Both of those things will decrease gastric secretions by the first two phases. So you see here, the third phase, the intestines are now in control of the gastric secretions. And once they deal with that first little squirt of low pH chyme and move it along, then the enterogastric reflex relaxes. The pyloric sphincter opens a little bit and a little bit more chyme gets through and the whole process starts over. It ends when there's no more chyme to get through. So when the stomach is completely empty, nothing will come into the intestines to trigger this reaction, and then the process is done. This whole thing takes about 4 hours. So when you eat a meal, it typically takes about 4 hours for your stomach to do what it needs to do, and then for it to pass little by little all of its contents to the small intestine. The stomach is constantly undergoing contraction, so it's going to move a little bit of chyme with each wave of contraction as long as it can get through the pyloric sphincter. Now, one of the questions I get from people a lot is if we're putting all these acids and enzymes out into the stomach and the stomach is made of tissue, why doesn't it digest itself? Well, there's a couple reasons, a couple features of the stomach that help to protect it from digesting itself. The first is the mucosal barrier. You have a lot of mucus that's being produced by those the mucosa cells, the surface epithelium, and the mucous neck cells of the gastric pits, and it's going to come out and form a really thick layer, which is going to keep those acids and enzymes away from the tissue. The epithelial cells in the stomach are also connected together by tight junctions. If you don't remember what a tight junction looks like, you're going to want to go back and look at the cell chapter from A&P 1. But it's basically where the cell membrane of two neighboring cells is actually fused together. So nothing can get down in between them, and those acids and enzymes can't sneak down between the cells and start damaging the underlying tissues. Another point is that the damaged cells are very quickly replaced. So the epithelium is replaced. The whole lining of the stomach is replaced every 3 to 6 days. Let's say something goes wrong, though. Let's say you're not making enough mucus, or it gets pushed aside, or something happens and those gastric juices do come in contact with the wall of the stomach. It's going to lead to a condition called gastritis. In this case, the gastric juices are touching the underlying tissue, and it's going to cause a local inflammation and irritation. It should go away. Okay, the mucus will be produced, or the food that's causing it will move along, or whatever the problem was, it should go away, and it may never happen again. If you have chronic gastritis, where you're chronically exposing tissue to these acids and enzymes, you can develop what's known as a gastric ulcer. And gastric ulcers can be dangerous because they do damage to the wall of your stomach. They can also bleed into your stomach and cause anemia. There's a lot of concerns with gastric ulcers. Gastric ulcers have been something we've known about for a long time, but we don't have a real finger on exactly what causes them. There's a number of different factors that can contribute to your likelihood to develop a gastric ulcer. You might make too much hydrochloric acid, in which case they might prescribe for you a medication that blocks the production of some of that hydrochloric acid. You might not make enough mucus. Now, that's a genetic situation, so that's where knowing that your parents suffered from gastric ulcers might tell you to keep an eye out for them. And then the presence of the bacteria Helicobacter pylori is also thought to contribute in some way to the formation of these gastric ulcers. For a long time, after they discovered H. pylori, they thought that it was the cause, because every single ulcer that they swabbed had this bacteria on it. But then they found out that lots and lots of people have this bacteria and don't have ulcers. So it's not necessarily the cause, but it might be something that once you start to form an ulcer can make it a lot worse. All right, moving on to the small intestine. Now we've moved the food through the stomach, and it's now in the small intestine, where we remember we're going to see digestion of all three macromolecules: the carbohydrates, the lipids, and the proteins. The pancreatic proteases break the big proteins down into very small peptides. These are all secreted in an inactive form, just like pepsinogen was the inactive form of pepsin in the stomach. These all have to be secreted in an inactive form and then activated out in the small intestine to avoid them digesting the cells that produce them. The three pancreatic proteases that we're going to talk about are trypsin, chymotrypsin, and carboxypeptidase. You also have pancreatic amylase being produced, which, just like salivary amylase targeted carbohydrates, so does pancreatic amylase, and it breaks down complex carbohydrates into what are called oligosaccharides. An oligosaccharide, oligo means a few, so it's basically the equivalent of a peptide. It's a small chain of just a few building blocks of carbohydrate. And then you have pancreatic lipase that's also being produced, and it breaks fats down all the way into fatty acids and glycerol. So of those three, only the fats are actually able to be absorbed after the action of the pancreatic enzymes. Oligosaccharides and peptides are too big to be absorbed, so they still have to be broken down more. Before we get into how we break them down more, let's just take a quick look at how we release those pancreatic proteases. So if you look here, you've got the pancreas sitting off to the side of the small intestine, and then this is the pancreatic duct that delivers the secretions to the small intestine. The pancreas provides procarboxypeptidase, chymotrypsinogen, and trypsinogen, all of which are inactive. Then out in the small intestine, all the time present, you have another enzyme called enterokinase. Enterokinase isn't a protease and it won't digest the proteins of the small intestine, but it does activate trypsinogen and convert it to trypsin when they're mixed together. The trypsin then serves double duty, acting as a protease, but also acting as the enzyme that converts the other two to their active forms. So the chymotrypsinogen is converted to chymotrypsin, the procarboxypeptidase is converted to carboxypeptidase. So it's kind of serving double duty. Then the trypsin, the chymotrypsin, and the carboxypeptidase go off and participate in digestion reactions to break those bigger peptides down or polypeptides down into smaller peptides. Now, pH is also an issue. I kept mentioning that it's a very acidic chyme that's coming out of the stomach, but the enzymes in the small intestine work at a higher pH or a more neutral pH. To neutralize the acid coming out of the stomach, epithelial cells in the pancreatic duct, the tube that connects the pancreas to the small intestine, release bicarbonate ions. So how do we control the pancreatic secretions? Well, again, you're going to see hormonal pathways and neural pathways. In the hormonal control, in the intestine, that acidic chyme is going to enter. And remember, that was the trigger for intestinal control of the intestinal phase of gastric secretion, but it's also important to trigger stuff that's happening within the intestines. So that acidic chyme is going to cause the release of two hormones, secretin and cholecystokinin, which you're welcome to abbreviate CCK. Secretin is going to tell the pancreas to release bicarbonate. Cholecystokinin is going to tell it to release all those pancreatic enzymes. Okay, so that starts to be released when the acidic chyme comes into the small intestine. Now, in the nervous control, this actually happens early. So this is like a preparatory phase that during the cephalic and gastric phase of control of gastric secretion, the vagal nuclei in the medulla send a signal through the vagus nerve telling the pancreas to start releasing its enzymes. So you've got both the hormonal control and the nervous control influencing the release of enzymes, but only the hormonal control triggers the release of the bicarbonate. That makes sense because while it isn't wasteful or harmful to release the pancreatic enzymes a little bit early, it would be irritating and unnecessary to release the bicarbonate early. So you really don't want to release the bicarbonate until the acid is there to neutralize. Another thing to consider in the small intestine are those movements that I talked about earlier, movements that both propel and mix and churn and enhance absorption. So there's three basic types of movements, two of which really function to mix and propel the food on a large scale, and one of which is much more small scale. So the first one is segmentation. Segmentation is also known as non-directional mixing, and it only involves the circular muscles. So when the circular muscles contract sort of alternately, where one ring contracts while the other relaxes and then they switch, they end up mixing the food very effectively. It works a lot like if you took all the ingredients for chocolate chip cookies and you put them in a big Ziploc bag and then you just squeeze the bag over and over and over again until it all mixed together. That's basically how segmentation works. Peristalsis is a directional kind of contraction that actually propels the food through the tract, and it involves a wave-like contraction of the circular muscles moving through the tube at the same time as the tube is shortening to enhance the distance traveled. And then last but not least, you have velar contraction. This is the more microscopic movement where neighboring villi, because of the action of the muscularis mucosa, remember both of these are the muscularis externa, because of the actions of the muscularis mucosa, we see those villi have an ability to go up and down next to each other. And when they do that, they circulate material in the space between the neighboring villi. Otherwise, it would just kind of fill up and pack in, and you wouldn't have all that nice surface area available for exchange. Now, after the contributions of the pancreas, you still haven't completely digested the carbohydrates and the proteins. The pancreatic enzymes completely digested the lipids, and part of the reason they were able to do that is because of the addition of bile from the gallbladder and liver, which breaks the fats into tiny pieces and helps those pancreatic enzymes to be more effective. However, the enzymes from the pancreas don't completely break down the carbohydrates and proteins, so you're going to rely on brush border enzymes as the last step in their digestion. Brush border enzymes are actually embedded into the wall of the brush border of the small intestine. You've got peptidases that break the peptides down into their building block amino acids, and you've got carbohydrases that break down the disaccharides into monosaccharides. So disaccharides, sucrose, maltose, and lactose. Sucrase is the enzyme that splits sucrose into glucose plus fructose. Maltase is the enzyme that splits maltose plus maltose into glucose. And lactase is the enzyme that splits lactose into glucose and galactose. That last one there, lactase, that's the one that a lot of adults lack. They don't have it. And that makes them lactose intolerant because they're not able to digest it. So I have a quick slide showing the breakdown of each of the 3 major macromolecules in the small intestine, just to summarize what's happening. Now remember, digestion started in the mouth and stomach, and those aren't included in these pictures unless you want to add them in. We're just talking about what's going on in the small intestine. So in the small intestine, these polypeptide chains come in from the stomach. The 3 protein digesting enzymes, pancreatic proteases, are going to break them up into smaller pieces that we call peptides. And then those are going to migrate over to the brush border enzymes, which are going to break the bonds between the neighboring amino acids and release them so that the amino acids can get absorbed across the brush border. This here is supposed to be a dipeptide, and even that is too big to be absorbed, so it would still have to be broken down one more step. When we look at the breakdown of carbohydrates, remember these haven't been digested very much at all because there was no digestion at all in the stomach. There was a little bit of digestion in the mouth, mostly to enhance flavor. So when they come into the small intestine, they're pretty much still long chain polysaccharides. Those polysaccharides are acted on by pancreatic amylase, which splits them into oligosaccharides, shorter chains. And then those oligosaccharides migrate to the brush border, where the brush border enzymes break them up into their monosaccharide building blocks, which can be absorbed into the bloodstream. And last but not least, you'll notice I showed this on a different scale because we're not interested in brush border enzymes for the fats. You've got a large fat globule mixed with the bile salts from bile, and the bile salts are going to surround smaller chunks of that fat globule to break them into what are called micelles. That increases the surface area for the action of the pancreatic lipase, and it's going to break them all the way down into their building blocks of fatty acids and glycerol. That one monoglyceride is too big to be absorbed, so it'll continue to be broken down, but the others are going to be able to move right across the cell membrane, right out the other side into the lacteal that would be over here. All right, just to wrap up quickly, I want to talk a little bit about some medical conditions of the digestive system. I picked 4 that I thought might be things you guys had dealt with or know people who have dealt with. All very different conditions. Heartburn is a burning, radiating pain that most people feel below their sternum or breastbone, and it happens when acidic juices from the stomach begin to regurgitate up through or bubble up through the esophagus because the esophageal sphincter isn't tightly closed. Some people, if you've never had heartburn before, you might think you're having a heart attack because of the pain that you experience, but really you feel those 2 things in very different places. And obviously this one can be cured by taking an antacid. If it's chronic, it can start to do long-term damage, and you may end up needing to take an acid reducer. Hepatitis is something we typically think of viral hepatitis when we hear this word, but technically it's just a description of a symptom. It means inflammation of the liver and anything that would cause that, but it is typically due to infection by a virus. There are several common hepatitis viruses, 3 that are very common in the United States. The other 2 are more common globally. Hepatitis A is the one that's transmitted by what's called a fecal-oral route, and typically it's from sewage-contaminated water or poor hygiene and hand washing. Hepatitis B and C require blood exchange or body fluid exchange, and was for a long time one of the higher risks was just blood transfusions, but we now screen those for hepatitis. Contaminated needles continue to be an issue for spreading hepatitis. And while there is a vaccine for hepatitis A and B, there is not one for hepatitis C. This is just a little viral overview of the 5 main types of hepatitis, showing the source of virus, how it's transmitted, whether the infection is chronic, meaning can it be eliminated from the body or cured, or does it stay in the body for a long time, and then ways to prevent it. So if we just look at A, B, and C, since those are the ones we're primarily exposed to, you can see, like I said, the source being the feces versus blood and body-derived fluids. The rate of transmission varies a little bit. Hepatitis A is not a chronic infection. Your immune system will fight it off and eliminate it, or you'll take medication and eliminate it. But B and C are. And they give you, in most, if an immunization is available, then pre and post exposure immunization can greatly decrease your risk or prevent you from contracting it. But in the case of C, where we don't have a vaccination, it's really just avoiding behaviors that could expose you to these viruses. Now, jaundice is a condition that can occur during hepatitis, but it can also occur during other situations where the bile duct that allows bile to enter the small intestine from the gallbladder and liver becomes blocked. And so bile pigments begin to build up in the bloodstream, which are eventually deposited in the under layers of the skin, making you look a little bit yellow. You can see in this top picture a person who's healthy with the normal hand versus a person with hepatitis. You can quite clearly see that the person with hepatitis has yellower skin in this picture, but if you were just looking at them, not comparing to another person, it's a little harder to see. One way that is very easy to see is that you look at the whites of their eyes, and they'll also be yellow. Okay, so while a person you might not be able to really determine without holding them up to somebody else for comparison, the eyes being yellow is a key sign that you've got jaundice. Now, gallstones are another interesting condition that affects this system. Normally, bile is produced and released into the small intestine and daily in association with your meals and the need. And it not only helps to emulsify the fats in our diet so that they can be digested more effectively, it's also a great way to help us remove excess cholesterol, because excess cholesterol is removed by the liver and added to the bile. However, if the cholesterol concentration of the bile gets too high, it can crystallize. So if you have too much cholesterol that you're trying to remove from the body in that way, or if you're underproducing bile, removing the right amount of cholesterol but under-reducing bile and changing the ratio, the cholesterol can crystallize and form gallstones. And it can form anywhere within the gallbladder, right at the opening to the duct coming down. Anywhere along there, a gallstone can form. Many times they just adhere themselves to the inside of the gallbladder, like you see here, and they don't move at all. So you could have gallstones and not know that you have them. But if one of them breaks loose and becomes stuck in one of the ducts, then that can be very, very painful. All right, let me come back to me here. All right, everybody. So that's it for our digestive system lecture. That's all the material. I'm going to make sure that I put up not just the video and the slides and the notes, but also that diagram, a tree diagram I told you that I would do for you, summarizing the layers of the digestive tract. And I think I have one other thing I was going to put up as well. So I'll try to get those done today and get them out to you. Try to stay warm and safe during the storm, and hopefully I will see everyone in class on Monday night. Thanks.